Okay, sorry. I'm enjoying the class here. I can chat with people. That's why the delay. Okay, at home it's me and the washroom and my room. Nothing to chat. Right. So we are now going to see. We are going to look at wide beam analysis. Okay, wide beam. Or wide flange, wide beam analysis. Come on, Eugene, wake up, wake up. I'm still asleep. Okay. Oh, my screen got nothing. I told you guys I'm sleeping, right? So the screen should have something now. Ta-da! Come on, show something, you cheeky sort. Go on. I'm having problem on my side showing screen down here. Come on. Is it on or no? It's usually the user, okay? It's nothing to do with the computer. Is it coming on yet? It's coming on down there, but it's not coming on down here. Oi! You all can see that screen down there. I'm not asking you to see the screen down there, okay? Go on. I'm having some technical very much difficulty. Okay, let me. Oh yeah. Oh, unbelievable. Hey, hey, stay. Okay, right. So we are going to look at the difference with now for the wide flange. I'm recording. Yes. Wide flange. Okay, we're going to look at wide flange. So now this is thin wall. So let me look at the standard one. Okay, the standard as in non-thin wall. Okay, how you find. So for non-thin wall, I'm in the wrong. Cheeky sort. I'm your favorite teacher. Yeah, right. Once you see your term test, you will aim your car at me. I'll tell you that. Okay. Okay. So this is a thick wall. Okay. So again, I want to show you some similarities and some difference. Okay. So now I want to find the stress at point A again. Okay. And I want to find the stress also the same about the same region, and this is point A. Okay. So for non-thin wall, come on. So for non-thin wall, to find A, the area that we'll consider is this area over here. The thickness that we will take is from here to here. Right? Okay. So knowing that this is our centroid, right? The formula we apply is shear stress is equal to Vy. So this has the Vy coming down this way over Izz Qz divided by thickness. So this thickness over here is this thickness. Okay. So for thin wall analysis, right, it's because of how we design the shear flow. I repeat again, it's because of how we have designed the shear flow, right, in such that we have how many terminals? We have 4 different terminals. 1, 2, 3, 4 terminals. So the area that we're going to take from the terminal to point A, this is the area. Okay? Because why don't we take more of that? Whenever at the terminal, the shear stress is equal to 0 at the terminal. Right? This is at the terminal. Okay? The shear stress is equal to 0. Okay? And how the shear flow, the Q1 is not related to Q2, and Q2 is not related to Q1. Yes or no? So for this case, right, Q, this is only Q. It's not equal to what? 2Q. Because from the terminal, it only released 1 Q. Yes or no? Whereas in the box beam, one terminal, it released how many Q? 2Q. Okay, so this is only 1 Q. Okay, so that is the area of concern, of consideration. Okay, you don't need to take the left hand side. So the shear stress now is equal to Vy over Izz. Okay, now the Qz is different. The area of consideration is different. Yes or no? For thin wall and thick wall, right? This one you need to take relative from the terminal to the point of interest, and then you divide by T, and down here 1, because 1 you only have what? Q. So this is where the dissimilar is. It's not the same. Okay, and then the thickness. Okay, this is the thickness. Okay, the thickness is perpendicular to the what? Shear flow. Are we clear? Okay, now there is also similarities. Okay, so what are the similarities? So everyone online, you guys are okay? Yes? If not, type or speak up. Okay? Everyone
All
online or here pay the same school fees. How much school fees now? I have no clue. How much? Is it free for you? You don't know how much is school fees now?
So please zoom out a bit.
A lot.
700. Yeah. So, yeah. So, yes, your question. This is because of the terminal. At the terminal, the shear stress is equal to what? 0. Then the terminal to point A is coming from the right terminal, yes or no? The left terminal shear stress is not going there, right? It's not flowing to point A, right? At the left terminal, right? The stress will come here and then you'll go down, right? That is why you don't consider what's going on with the left-hand side. Yeah, thick wall you do. Okay, thick wall you do, because thick wall is just relative to the y distance, right? It's just relative to the y distance. It's thick wall is just relative to the what? Y distance. Yeah. Wait, I just answer yeah to just say yeah. What did you just say?
So I don't put any terminals on here.
Yeah, no. Sorry, I do apologize. You know, when the brain all of a sudden like, let's get it going. I do apologize. Okay. Sometimes I get yelling from my wife, from my current wife, for doing that. Okay, I just say yeah. They say, what do you say yeah to? Not a clue. Okay. Then you get yelling. Okay, you get hell. Right. So that is the this, but there are also similarities. Okay, so I'm going to again. So now, okay, so now I try to wipe this out. Oh, yes. Okay. So now the similarity is, what if now, right, we want to find at point C. Likewise over here, we want to find at point C. Okay. So at point C over here, the area of consideration now is this. So if you look at thick wall, the area of consideration is this. So you have this, and then you have this. You have to consider this whole area. The same thing, okay? The Q1 and Q2 are coming together. And then you have this. Same thing. So for both sides, now the thickness are the same. This is the thickness, and this is the thickness. Okay? So now what you do is the shear stress is equal to VQ, okay, over IT. The thickness is the horizontal direction. This one, the shear stress, is equal to VQ over IT. Okay. Now, some of you will tell me Q1 plus Q2 is 1Q down here. Okay, it's just Q down there. Because all this is relative to your first moment of area. If you don't understand the concept yet, don't worry. We are going to do another example to make you understand what is going on. Okay? Right. I know this last bit is a bit confusing, but bear with me. Okay? I will do an example, and I hope you'll be clearer. And this example, I have 2 more examples to do. Okay? Depending on time. Okay, if time don't permit, I'll just do one. Okay, so the example I want to do is this one. Okay? So I'm going to copy. Okay, this is the example I want to do. So this is our example number 2. Let me zoom out so you can see better. Example. Knowing that a given shear flow V causes a maximum shear stress of 10 KSI in the head-shaped extrusion. Determine the corresponding shear stress at point A and at point B. So I will draw our transformation first. Okay, later on, I need to go to PowerPoint for a bit. Okay, just ignore me. Okay, take a break. Okay, I need to go PowerPoint, do something. And I need to draw a box. Okay. So we have a head extrusion. Okay. Based on geometry, the centroid is exactly at the center, 1.5. Okay. So this is the centroid. Okay. That is the centroid. So now I will construct our transformation. So this is your Y, and this is your Z. Okay.
Excuse me, sir.
Yes.
For the centroid to be in the middle, doesn't the shape has to be symmetric at both top and bottom?
If you look at the shape at the top and bottom, no, okay.